All right, so it's the usual thing. Need to get rid of this. All right, so welcome to lecture 7 of our deep learning class. So I hope in the last lecture we discussed a lot of different things to kind of lead us towards actual like using deep learning libraries and not doing everything by hand anymore. We discussed optimizers. So we had our different types of optimizers, just stochastic gradient descent. We discussed momentum and Atom as a good default optimizer. Then we discussed a little bit about, okay, once you want to go and build deep networks, you need to be careful with the initialization. So it's not only kind of that you have an optimization algorithm, but it's also kind of where you start so that learning becomes feasible. We discussed some tricks to do data normalization. And so now we'll kind of build on this a bit and then go towards a more specialized class of neural networks that is not only kind of feed-forward multi-layer perceptron. But before that, from the exercise, I hope you kind of managed to train a neural network. So this now starts to feel a little bit like something you would expect a machine learning system to do. It's not only separating points on the two-dimensional plane, but it's actually doing handwriting recognition. And this is one of the famous use cases that worked actually with deep neural networks early on. And so one of the pioneers of deep learning, Yann LeCun, he did this in the 90s. It was used to scan checks because in the US, for some reason, they use checks, even until today. And so it's important to do kind of optical character recognition. And so now this feels much more real. So you can basically say, okay, you're scanning this 28 by 28 pixel. There are no rules that you are, I can, okay, just for you. All right, let me try that. And then we'll. All right, so let me see. Downloads. All right. So. Where are we? Here. All right, there you go. Okay, so now we, so there are no rules kind of as a human that you're constructing, but it somehow does the right thing. And so if it's like clearly a 9, it will have, so you see like the posterior probability. So this is what we, abstractly talked about, like variational inference. So we want to have the posterior, what is the digit given the data? And so if it's a 9, there's a very high probability that it's a 9. Right, and then you might see, okay, there's also a non-trivial probability at 7, which if you look at it, might actually be kind of convincing because it kind of the way this particular 9 is written actually looks a little bit like a 7. Then there's also a case where you have very weirdly written digits, and there's like a large confusion, and there's lots of probability everywhere, and so it kind of does the right thing, and so that's kind of your first, machine learning or AI system. Okay, so then now with the stuff that we discussed in the last lecture, we have a pretty good toolbox to build deep neural nets. And then we started adding like these things where, okay, so we started with linear layers. So, okay, you want to, find new features. And then we started adding nonlinear activations. This was important in order to kind of break the linearity and not, because otherwise just adding a bunch of linear layers is the same thing as one big linear layer. And now we add things like batch count, where you can see kind of pattern emerging that you have like larger blocks, and then you're repeating these blocks in a kind of like a stacking type of way in order to get kind of deep systems. Okay, so there's one more thing that we didn't discuss last week, and so I wanted to quickly touch on this because this then leads us to the next topic. So the basic question in well, like the basic setup in neural networks is that we have this hypothesis set, so the family of functions that we're searching through now, right? And now we are learning, okay, we want to add kind of more blocks in order to get more expressivity and so on. And so one of the key questions is, okay, now once I start building deeper and deeper networks, how does this family of functions evolve, right? So hopefully it becomes bigger because we're adding parameters, but what exactly is going to be this new family of functions? And so we'll discuss this a little bit. And it's part of the question, that touches on this question of whether or not going deeper is always better, right? And so we discussed this question a couple of times already in this lecture, and so there were various answers. So, in the classical machine learning point of view, the clear answer is no, because we had like this bias variance trade-off in order to avoid. So just having like a humongous family of functions is not going to help you, because then this just leads to overfitting. And so you wanted to trade off bias and variance in order to kind of control what the generalization error is. So as you go larger and larger, then your train error becomes low, but then at some point your test error goes up again. Then there, like also actually in the first lecture, we already discussed things like deep double descent. So this is the so-called interpolated regime. What does it mean? That's an interpolated regime. It means that it perfectly predicts all the training data. And so there's zero train error. And so this is kind of this wide area, kind of the super over parameterized regime. And so it turns out that with gradient descent and various other properties of neural networks, actually it might happen that it is actually true that deeper is always better, right? But so these things are kind of sometimes in conflict with each other, and it depends on the application. But they're like these two answers that we have. But there's a different interesting effect where you go to deep networks, and so this is called degradation. And so this is the effect that bigger networks perform worse, but they perform worse not only in the generalization, like in overfitting. So in overfitting, the deep network produces is very good at the training data, but then starts becoming worse and worse in the test data. Degradation is the effect that once you go to bigger and bigger networks, actually it's harder to train, or like it loses some kind of the solution that it found previously with a smaller network. And so you can see here, so on the left-hand side, you see kind of two networks with 20 layers and 56 layers. And so this is the training error. And you can see that the 20-layer neural network performs better. So the training error is lower than the bigger network. So that is a bit unintuitive. You would think, okay, you have like a bigger function, and so at least on the training data set, it should somehow through like stochastic gradient descent and overfitting at least be much better on the training data set. And then it's maybe expected to be worse on the test data set, but at least on the training it should be much better. But it turns out it's getting worse, right? So something is happening. And then on the right hand side you see the test error. And so there it's also worse. This is maybe something we expect, but what's a bit surprising is this degradation on the training performance. And so what is happening here? And so basically it's all about how we grow our hypothesis space. And so what seems to be happening is somehow like a previously good solution that we knew that we can discuss. So this so what we want to have is kind of like the left-hand situation and not the right-hand situation. And basically what we can look at is, okay, if we just stack two layers on top of each other, so basically there are two functions, right? So in the philosophy of deep learning, the first function is kind of preparing the features for the next function. And so the overall network, which is the f prime, is basically just a composition of g of f of x, right? And so what we can look at is if we just kind of use our initialization tricks and so on, and we look at, okay, what is the relationship between the output of f of x and f prime of x? There's no relationship, right? So somehow, it forgets kind of what f of x was, and it starts doing its own thing, right? And so that might be fixed through training. So this is just an initialization, but it means that your kind of your composition, destroys a little bit this correlation just from the way the network is structured. And but what we can also exploit is that in our initialization discussion, we kind of realized that getting a network that is kind of on average predicting 0 is quite easy, right? And so with our initialization, if you just kind of take your kind of simple linear layer with the nonlinearity and then another linear layer, and you just plot kind of what is the predicted output of this for some random input, it kind of predicts 0, right? And so getting 0 is not so difficult. And so what we can do is basically something like this. And so this is called a residual connection. Instead of saying, okay, we don't put any constraints on what this g of f of x is going to be, we just stack different functions. We force a certain structure for what this g of something is, right? And the structure that we're forcing is that it kind of starts with the f of x, and then it computes what's called a residual. It computes like a delta to the previous known solution, right? And so this will ensure that it will not kind of, if this r of f of x kind of gets initialized at 0, kind of at a simple initialization, it will just reproduce the original solution, right? So it's not forgetting the previous solution. So that's a nice kind of idea. So you can see if you do the same thing and kind of look at what is the correlation between f of x and f prime of x, which is our particular way of constructing g of f of x. Then it's kind of the old solution, but just a little bit noised out, right? And so if you kind of design this as a computational graph, what is happening is that you have basically this residual connection happening where you go kind of from the, so this is actually, let me see, so sorry, so I'll need to fix this. So you basically do like a skip connection like this. So basically you take the old result, right, and then you add you do an addition between the old result and this residual result, and by this you basically just reproduce what you had before. But then with the option to learn something more complicated, but this is your starting point, that you just say, okay, maybe the shallow network was already doing a good job in terms of data representation, so I'll just kind of work on top of this. Okay, so then basically what is happening is that with residual connections, you kind of are in this space on the left-hand side where the function spaces are nested. So it's clear from the setup how these residual connections are designed, that the solution f of x is trivially included in the family of functions where you also have an r as a residual, because for the case where r is 0, then you just reproduce this old function. And so you basically grow like a nested shell. As you add these residual connections, you grow and grow these function spaces. And so you don't run into this issue where you're shifting the function space. You're enlarging it, but then shifting, and then you might drop previously known good functions. Okay, so then what's nice with residual connections, basically neural networks can become arbitrarily deep, right? So it doesn't really matter whether or not you're stacking 100 layers or 1,000 layers or something like this. You can always, if you're kind of adding these residual connections, there's a signal that goes all the way through all of these skip connections, and then we'll just reproduce the original function, right? And so so this is sometimes also called like a highway connection, and there's a architecture called the highway net that kind of preceded this idea a little bit. So it's basically a way to go to very, very deep neural networks, and every kind of additional block is just kind of like a new additional correction to the previous known solution. So you're building up kind of your solution step by step as you're adding depth. All right. So what does this have as an effect of training? And so here we see kind of from the original paper that introduced these ResNets, a plot where you see kind of on the left-hand side, this original construction where you didn't have residual connections, and then the deeper network. So you have in red, the 56-layer network is performing worse than the 20-layer network. And then once you have a ResNet, you can actually go, you see the 20-layer network is the worst. And then if you go to 110 layers, it becomes better, right? And so this is usually what you would expect, and you don't see this degradation effect. And then just for kicks, in this paper, they also basically go to like 1,000 layers, right? And so it's making the point that then this idea of depth is not really kind of like a big issue, because you're like reimagining it as more like a correction to the previous known solution. And so now in modern neural networks, you see some constructions like this where you have like hundreds of layers that go very, very deep. Okay, so then basically, so where do these ResNets become important? So the main use case for these residual connections or these very, very deep neural networks is in computer vision. I think I mentioned already that computer vision is one of the main driving areas for machine learning, because it really kind of touches on this idea that you want to kind of learn something or process raw data, which is like your perceptive data that you have hitting your eye, and you want to kind of process this similar to your MNIST data sets. The idea you have raw pixel data and you want to extract some high-level concept from it. And so this is where residual or so-called ResNets really shine. But they have one more important architectural choice, which is going to be the main topic of this lecture, is convolutional networks. So they have computer vision is driven a lot by convolutional networks, and so we're going to talk about this in the next hour or so. Okay, so yeah, as I said, so the convolutional networks are the main driving force behind computer vision, and computer vision itself is the main driving force behind a lot of these kind of advancements in machine learning. Long before you had things like for drug discovery and these things, or like machine learning for physics, there was the real breakthrough in this ImageNet moment that I mentioned 10 years ago was in computer vision. And so there are two important ideas for convolutional nets. So basically, they solve this question on being able to process arbitrarily large inputs without kind of having to grow your network to arbitrarily large dimensions. And it will also, it will be the first example of adding domain knowledge into your network that we think is important. And so this is going to be translational equivariance and invariance, which kind of speaks to one of the core properties that we think is important in vision. Okay, so then let's start. How do we get to convolutional nets? And so basically in a standard machine learning, like multi-layer perceptron, right? So what we have is that the number of connection, if you have like a layer going from 3 dimension to 3 dimension, is going to grow quadratically, right? Because there's a weight matrix in the middle. And so you need to go from every node to every node. And then you have like a quadratic number of connections, right? And so now, okay, so for MNIST, it's maybe fine. So for MNIST, you had 754 inputs, right? And so what is the weight matrix? So when you have like from 754 to like 200 neurons, I mean, it's already a quite sizable number of connections, right? And it's like a tiny, tiny little image, right? And so it's clear that you're not going to process a megapixel image with this, because the typical image that you have, in your favorite city here is like millions of pixels, right? And so in order to get to the point where you are maybe also where like in MNIST, it was very easy to see the individual pixels. And here you need to zoom in multiple times to kind of see the original pixels. And so now let's say you just want to do like a mapping into some feature space from 1 million dimensions to 1 million features, that seems reasonable, but then you have 1 billion connections, right? And so this is very, very unfeasible. This will not work. So you'll not be able to kind of train at least easily like a neural network with 1 billion parameters. There are networks with 1 billion parameters, but they're not used to just kind of classify an image. The billion parameter networks are, so yesterday there was like a new release on the very powerful language model. These are like the billion trillion parameter models, but for computer vision, it's not necessary to do it because we can exploit some of our domain knowledge in order to shape the network in a way that it will be much more parameter efficient, right? And so in this bias variance trade-off, it will basically move to the left. Okay, so then one of the things that we can put in and that we think like how vision works is if I look there or look there, probably the same type of processing is happening. In order to understand what's happening in this corner of the image, I don't need to really know what is going on in this corner of the image, right? And so this is somehow kind of what we think is how our vision works. And so maybe to classify globally what's happening, it becomes important, but to just kind of recognize which objects are where in which picture, you only need local processing. And so one thing you can do is you can basically start pruning away connections. So instead of just having every node connects to every node, you can say, okay, every node only connects to its neighborhood, right? And so this is exploiting, this idea of local processing, but it's also exploiting that in an image, there's a very regular pattern. So you have pixels and there's a very clear notion, who is my neighbor, right? And so it's very easy to define what is a local neighborhood. And then you say, okay, I'll only have connections to my local neighborhood. And so now you basically reduce the number of connections that you have instead of n times n, you have L times n, where L is the size of the neighborhood. So you went from a quadratic increase in the number of connections by the image size to a linear increase. And so that's already pretty good, right? Okay, so then but we can do even more. So then the question is, okay, how do I process like one corner of the image and how do I process a different corner of the image? Probably your eyes are not and your brain are not changing, right? And so what seems reasonable is that the processing that happens in each corner of the image is probably the same type of processing, right? And so this is we can implement in convolutional neural networks as this idea of weight sharing. So we have only these few connections. So every node is only connecting to 3 nodes, its local neighborhood. But then recall that for every weight, basically there's a number, how strong is this connection, right? And so what we can say is, okay, it seems reasonable that like these types of processing dynamics on how you go from the input to the output should be roughly the same kind of in one corner of the image and the next corner of the image. So basically, if we just kind of color code what the actual weight value is going to be, we can basically force that the weight value for all of the connections that go kind of one to the right or one upwards is going to be the same value. The one that goes like straight across is going to be the same value. The one that goes down is going to be the same value, right? And so now you have dramatically decreased the number of actual parameters of or like degrees of freedom because now you only have 3 degrees of freedom, and then you're just reusing all of these weights across the entire image, right? And so you don't even have any linear kind of growth anymore with the size of the picture. It's just constant, right? And so that's even better. So then the question is, of course, okay, how do you get complexity? And so we will discuss this one. So this is a kind of important consideration. It's really deeply rooted in the way we think information processing happens. It's local, and probably the processing strategies of the car is here or the car is there probably should be doing the same thing. Okay, so then we have like this picture on the left-hand side where we have like all of these different color-coded weights. And so the way you can kind of visualize what is happening here is that basically you have like a little box with these 3 weights, and then it's sliding across the input. And then for every output, like this box is always pointing to one output node, and it's kind of touches on a certain number of like local neighborhood around it. And you have like a field of view, and you're looking into your neighborhood. You have like a certain like instructions on how to process this local neighborhood, and then this will produce your output. And so you just repeat this rule, and you do it for one neighborhood, you go to the next neighborhood, you go to the next neighborhood, and then you always kind of apply the same type of rule, right? And so, for example, you could imagine, okay, let's say, okay, this is not going to work with like 3 edges, but like you can imagine, I have like a cat detector, so I want to see where's the cat. I can just I have like a certain fixed rule on detecting a cat, and so I look in this kind of window. Is there a cat? Yes or no? Is there a cat? Is there a cat? Is there a cat? And then you just kind of slide through your entire input. Okay. What's kind of interesting is that this now becomes completely independent of the size of the input. So whether or not your image is kind of 10 by 10 pixels or 1,000 by 1,000 pixels, first of all, like the number of parameters doesn't change, but also like the processing rule doesn't really change. It's it's workable for a variable number of inputs, and so that's also very nice because you don't need to retrain your network. In the MNIST example, if you had like a fully connected deep neural network, it's 28 by 28 pixels. So let's say you buy a better scanner and this scanning is as 50 by 50 pixels. Now you have a problem because you need to retrain your network, right? And so with these convolutions, basically you're able to adapt to the size of the input as well. Okay, so then this is what we basically call like a one-dimensional convolution, and we can translate this into kind of mathematical notation. So basically, the output is going to be some weighted, function of the input. And so usually, what we had in like a normal multi-layer perceptron was like a big matrix multiplication over all inputs, and then you had like a connection from all outputs to all inputs, and so you had like a big matrix like this. And so now basically what is happening is that we're restricting the sum. So it's still a weighted linear combination of inputs, but the only inputs we're considering is not like all 0 to n, but we're just kind of looking at a certain neighborhood, right? And so we're saying, okay, we have a certain weight, and then we only look at, kind of +1, -1, and 0, right? And so it's like the 3 inputs that we have. Okay, and then we said we had our second step. So this was kind of the pruning stage, that we killed certain connections, or we basically forced them to be 0. And then you can say, okay, now we say we want to have the weights independent of the specific location where I am. And then this is kind of simplifies here, where the weights are independent of I. So there's only one index for like, okay, in which direction in the neighborhood are you looking? And then in the end, what it starts looking like, it's like a discretized version of what you might know from calculus as a convolutional integral, where you have like a sum or like an integral over a function where there's a certain weighting function and then like a shifted input. Okay, so that's why they're called convolutional neural networks, because they're kind of discrete convolutions of signals, right? And so it's there's an entire field on signal processing on how to design these convolutions. Okay, so just as an example, what type of convolutions you can have. And so now basically only freedom you have in like a convolution is, okay, how do you choose the numerical values and how strong these edges are going to be? And depending on how you choose these weights, these convolutions are going to implement a certain type of processing, right? And then basically, so let's say we have our convolution, we have 3 weights, -1, 0, and 1. And the input that we're processing is kind of like this input that is constant at some high level, and then drops down to like a lower value. And so we can see, okay, how do we now do this convolution? Basically, we need to say, okay, I want to do like -1, which is my filter, times whatever the value is at this point. And so that's -1 times 1 is -1, right? And then you shift this to the right. And then as you're seeing kind of what the output is going to be, then you see that it's kind of it's a 0, then it's -1, -1, and then it goes to 0 again. So because here you have, do you see the mouse here? Can I show my mouse? Okay, whatever. But you can see, okay, so like the first one is, so we're looking at, like the middle filter. So 0 times 1 is 0. And then you have -1 times 1 times 0 times 1 plus 0 times 1 plus 1 times 1. And so you basically get -1. And so it basically works out. And so now you can kind of see what is happening kind of from the input to the output. So you have like this setup where it starts from a kind of high edge and then it drops down to a low edge. And then what is happening on the output side? So once you process it with this convolution, basically what is happening is it has like a 0 response everywhere where it's constant. And then, but at the point where there's a transition in terms of like what the value is, so where there's a contrast in the input, then it actually has like a signal, right? Because there basically the signals are not balanced, right? So if it's in a case where there's like all ones, it will basically, because you have a -1 and 1, it will basically cancel each other out and the overall response is going to be 0. Right? If there's an unbalanced input, so it's not a constant input, then it's going to produce a non-zero output. And so it's kind of like an edge detector where it will kind of produce a signal at the point where there's a transition in the input. And so then you can also do it the other way around. So you can also have like a ascending edge. And so you can see it's the same idea. You have a kind of input that is piecewise constant, and you have an output where there's a signal at the location where there's a kind of transition in the input values, right? And so that seems useful to have, and we can kind of see where this leads us. And it becomes much, much more interpretable once you go to kind of two-dimensional convolutions, and we can extend the same idea of like, passing a single window across like a one-dimensional array. We can extend this to a two-dimensional array. And so here it's the same idea. You have like a field of view on what inputs you're considering, and then the thing that you're kind of processing this field of view with has like a certain weights, and these will produce your output. And so you have kind of like a local processing rule, and we say, okay, for this particular output pixel, I will look at my neighborhood and I will apply some rule to it, and then I will have some output value. And so you do this basically for every type of local environment that you have. And so you can kind of go here and then this window and then this window, and then you go down and so on, and you can basically just scan over your entire input, and then it will always have like a local response. Okay, so what does it mean? So I said we have like an edge detector, and so we can basically extend this idea of having an edge detector that goes from -1, 0, and 1. And but then we basically just extend this kind of 3 times in the second dimension. And basically what we've seen is it will respond to like a change of input that goes from a high value to a low value. And so once you process, for example, your MNIST digits with this particular set of weights, then you see it will pick up the vertical edges, right? And so it's nice, but it will forget it, or it will not pick up the horizontal edge. So you see in the 7, there are 2 edges. There's one horizontal edge and the vertical edge, and kind of doesn't. So this particular filter doesn't really recognize that there's a horizontal edge, because the weights are chosen in a way to only respond to changes in inputs kind of in the horizontal dimension. And so then you can do it depending on what you do. You can also do horizontal edges. So if you flip this around, it's still kind of this -1, 0, 1. And then you can also do kind of horizontal edges. And so it's clear, yeah. Well, so I produce them like this. So I take my kind of weights, and then I do this convolution type step. So I slide over my image with my certain kind of environment, and then whatever the weights are, I kind of compute all of these 9 pixels into some output pixel, right? And this is then how you compute the output, right? And so it's kind of clear that, okay, just having one type of detector is not going to be useful. You probably want to have Like if you want to process images, you probably want to know about the vertical edges and the horizontal edges as well, right? And so you probably want to have multiple of these kind of convolutions. And so now you're scaling your network. So for every convolution, it's a constant number of parameters, but now you want to have many of these detectors that do different things. So some, see the horizontal edges, some the vertical edges. You can also do things like inversion. So if you have like a weight that is like 0, it basically ignores the environment and it's only kind of flipping the central pixel. Then it's just basically inverting the picture. You can also do things like blurring. So you might imagine, okay, if the task of the neural network is to kind of assess some global structure, maybe the details are not so important or, are actually hurtful. So you want to have like some kind of rough version of the image. And so you can imagine that, such a blurring filter would also be useful. Okay, so then basically what it means to have a convolutional neural network is that instead of putting these things by hand, so now, I mean, it's the same kind of idea. So I can kind of put these rules by hand. So if I know, vertical edges are important, horizontal edges are important, but I mean, quickly I run out of ideas. So I guess I could try to do like a filter on curves and so on, but I don't really know how to design them, and I don't really know, which things are important. And so the idea behind the convolutional neural network is to basically just set up the structure of local processing and kind of invariant processing on different ends of the picture, and then let the machine learn what the right filters are going to be, right? And but now we are kind of in this trade-off. Okay, how much domain knowledge are we putting in, and how much do we leave up to the machine? So now we already have quite a bit of structure where we think our domain knowledge is important, but then there's a quite sizable amount of things that we leave to the machine to figure out itself. And so we are kind of providing the scaffolding, and then it's being filled out by the training or the learning process in the meantime. Okay, so then there's so convolutions is nice, but there's a certain type of rule on how do you kind of process this input. And so we said, okay, how do you place these windows? So this is also an important choice. And so now basically, if you go step by step, then you kind of produce like an output that is smaller than the input. And so if you only want to kind of do like edge detection, you basically just want to kind of process the image without reducing the amount of information, then what's useful is to do something called padding, where you kind of add dummy inputs at the edges so that the input size and the output size are going to be the same. And so this is exactly kind of what happened here. So you'll notice that the size of the image didn't really change. And so it's only kind of doing kind of transformation of the finding good data representations. And it's the same thing that we did also with machine learning or with multi-layer perceptrons, right? Where if you can definitely have like layers that have the same number of output dimensions and input dimensions, they basically purely act as like a new lens on the input data. And it's not necessarily about reducing the dimensionality of the data. All right, and so what exactly is the input or the relationship between the input dimension and the output dimension then also depends on what type of step sizes do you make. So do you go like one by one, or do you do like bigger steps? And so this is what you can see here. So if you go like one by one, you are kind of reducing your dimensionality not so much. If you have kind of bigger steps, and then you have like bigger reductions of dimensionality. And for example, if you move your window kind of in completely disjoint regions, you're basically dividing your entire input by the size of the filter. Okay, so then now, as we said, we want to have multiple of these types of filters, because we assume that multiple of these filters are useful, right? So you want to have these horizontal edges, vertical edges, maybe you want to have blurring and so on. And so basically the way that you can design what we call a convolutional layer is to have multiple of these filters kind of stacked behind of each other. And they basically act as what we call channels. So in a normal image, you have like red, green, and blue, and they all contain different information. And now you can kind of extend this notion to features of the image. So you can say, okay, I have like an entire deep stack of basically the same image, but one channel has the horizontal edge, the next channel has the vertical edges, the next channel has some blurred version, the next channel has maybe some curves, and so on. And so you basically stack like multiple copies of the image, but in a way where each channel is highlighting a different feature of the original image, and then this is going to become the input to the next layer of processing. And this is exactly what we want the deep network to do, is to basically prepare the image or the data in a way that then at some point makes the decision-making process much easier. Okay, so then, just having kind of large inputs or invariant inputs in this, the size doesn't change, it doesn't help. So at some point you want to kind of reduce the size in order to make some statement on what is like globally happening in the image. And so this is what is happening with pooling, and it's the same type of idea where you, like in multi-layer perceptrons, you often start with a very wide layer. You had your MNIST image with 700 inputs, and then at the end you want to somehow get to one input, right? And so you want to somehow reduce the dimensionality step by step in order to kind of funnel the information to the output node. And so this is then what is happening with pooling. So pooling is a particular operation that is basically only there to reduce dimensionality. It's not a learnable operation, so there are no parameters kind of associated to it, and it's similar to like a non-linearity in multi-layer perceptrons. There were also no parameters associated with the non-linearity. It was just like a fixed type of operation that had like a specific role, right? And so here with pooling, one thing you can do is basically you can say, okay, I want to look at my certain field of view, and I want to do like apply like a fixed rule on how I go from, let's say, 4 inputs to a single input. Right, and so this is, and this will basically half your dimensions in every dimension. You can imagine you just need a few of these, and then you'll kind of reduce from a megapixel image to a single output node. Okay, so there are different types of pooling operations that you can do, and so there various things that you might want to do. And so one is like maximum pooling. And so this is kind of just saying, okay, is there a signal, yes or no? And then if there's a signal, I don't really care what the other signals in the kind of field of view are doing. I just say, yeah, let's go. And so this is like an activation function. Okay, if it's somehow above threshold, you just say, okay, I fire. And so within this field of view, I saw something. Right, and then there's also average pooling. If you want to kind of, for example, like have like a assessment on like the color, you might want to do like some kind of average, because it will kind of capture what the overall property of this entire field of view is, right? And so you can imagine there are different ways to do this type of pooling operations. And so here is an example of max pooling. Where basically we had our simple like field of view, like 115, 510. So what is going to be the output? It's going to be 15, because that's the biggest number. 4, 3, 12, 13 is the same idea, and so on. You basically just look into your field of view, you take the maximum value, and that's going to be the output. And so it's kind of like a summarization of whatever you've seen in the input field of view. Okay, so what's also kind of like a secondary effect of pooling is that once you do like iterative pooling, you can kind of see like what is like all the different kind of pixels in the original image that contribute to a certain output node, right? And so if you have multiple pooling operations, the effective field of view that kind of affect what is the output in this highlighted output pixel on the right hand side is going to be a larger field of view in the input, right? And so the later layers kind of see more of the image than the early layers. The early layers, they are only really doing local processing, and the later layers, they're doing more and more and more global processing, where they kind of combine information from different fields of view, and then you start maybe putting together some information that is classifying what generally is in the picture. right? Where like a local processing will only kind of tell you, okay, what is happening like in this local neighborhood, and that might be an edge, right? But you're not necessarily interested in, okay, is there an edge in the picture? Of course, there's an edge in the picture. You're interested, is there, like some object? And so that is local information. And so this type of hierarchical processing is exactly what we want to do. And so pooling achieves this by basically funneling again the information from very diverse regions into a certain output node, but it's still kind of a structured way to funnel this information. It's not completely local. If you had a multi-layer perceptron, it will basically, every output node will have a connection from every input node in the original input. And so that is kind of information overload. And so here you have a much more efficient way to direct the flow of information. Okay, so then we can look closer at max pooling a little bit. And so one of the interesting properties that is now emerging from choosing this particular way of pooling operation is that it adds kind of approximately what we call translation invariance, right? And so basically, what do we mean with invariance? Invariance means the output doesn't change, right? And so why doesn't the output change? So we can see, okay, what is happening if we shift the entire input? So we translate the entire input to the right, right? So what is the output going to do, right? And so as you see, it's not doing anything, right? And so we we can shift the input, and the output signal is going to be the same. And so this is also something that we think is important, and we'll get to this in vision. Because so it's often the case that you want to somehow, the answer shouldn't depend on certain details that we think are kind of by chance or symmetric. So if you want to detect something, it's good if you're not kind of so beholden to the details. And so you can see that this is constant for quite some time. It depends a bit on the field of view, and it depends, of course, on the input. At some point, this flips, but then there's also kind of again a phase where it becomes invariant, right? And so the more and more you kind of add these layers, the more and more translation invariance you're building into the network. And so then overall, it's going to be translation invariant globally. Okay, so now we're ready to basically build convolutional nets. And so we just use, like the standard deep learning philosophy that we have. We discussed that, if you want to do kind of classification of some input, you can either do like hand engineer features. And so for this example of flowers, it was basically like the size of the leaves and so on. And so then you have like a shallow network that will do a classification. This is the classic machine learning, but deep learning was all about kind of going from raw data to the final answer. And so we want to hierarchically build up different features and process the information that is helpful for the final high-level task of classifying, okay, what type of flower is this? And so we can basically use now our kind of new tool of convolutional nets in order to achieve this. And basically, what we might do is that we're trading off. So we want to go from a very kind of big input in 2D to like a final output. And in order to do that, we're basically trading off like the number of features, so the number of statements we can make about like a certain field of view against the dimensions of the image. And so we start out maybe with the input image, which is maybe large, and then only has 3 channels. It only has like color information, right? But now we say, okay, I want to add like edge information, curve information, texture information, and so on. So I'm stacking a lot of these things, and then I'm summarizing them. And so I'm kind of reducing the dimensions in in the kind of spatial dimensions, but I'm adding the number of things I can say about the image. And so you go deeper in the channel dimensions. And so you can kind of see like a typical setup looks something like this. You start with a shallow but a big input, and then later you basically turn it into kind of like a cylinder where you might only have like a single output, which is what we want. But then it includes basically global information about the entire input picture, right? So if this is like a single dimension, this will have information from all fields of view, funneled into it. But then you have multiple things statements that you that this output makes about the entire image, right? So it might say, okay, the overall color is this, there's this object in this image, or and so on. And so now, once we have like this entire list of summaries of what is kind of in the input that might be this image, now we can basically do our final classification. So we have like some high level information about the image, and then we stick it into a standard multi-layer perceptron. Now we don't need to be fancy anymore. We can just use a standard like simple neural network. It might not even need to be super deep. And then this will do the final classification. So this is exactly the type of setup we have here. So we have like a phase that is only kind of data processing and preparing for the final answer. And then the final thing is then like a simple neural network, because you like spent a lot of work in preparing the data. And then you have your final output. And so it might tell you, okay, there's a cat in there or not. Okay, so then how do you do a CNN merge? So, we did a lot of work in, doing gradients and so on. And so, finally, we can just kind of rely on what's available in the community. And so we still use like this nice toolbox that Torch gives us in order to build up sequential networks, but we're now using a different layer. And so this is this two-dimensional convolution layer. And so basically you say, okay, how many input channels you have, so how many color channels. So like in a photograph would be 3. For MNIST, you only have intensity, right? So you only have like a high value or a low value. And then you say, okay, I want to, how big should my field of view be? And so this is what you say with kernel size. And then with the output channels is, okay, how many filters, how many pieces of information do I want to kind of extract for every local patch in the image? And so here you're extracting 16 edges. So 2 of them might be horizontal edges and vertical edges, and then there are 14 more types of things, and that you might not actually know what they are, but you basically provide slots for the machine learning system to fill this with like useful representations of the input. And then you do the standard thing. You still do like a nonlinearity. You do your max pooling, and then you kind of reduced your image a bit, because you pooled, and now you do the same thing again. So now you go from 16 channels, and then you're converting them again into 16 channels. And so this is similar to, you're not adding the number of kind of slots, types of information you want to have, but then it's only like a transformation. And then the network is able to correlate like different, is there like an edge in this direction and an edge in this direction? This might lead to like a curve detector, right? And so then you do the same thing. You have like another convolutional layer with 16 input channels and 16 output channels. But now you might have like a smaller kernel size. And then you have a nonlinearity, you pool again. And so you start stacking the same way that we stack like a multi-layer perceptron, but now you have kind of built in like this idea of translational invariance and local processing and weight sharing and these types of things. But like from a programming point of view, kind of so imagine we need to do this now by hand and like doing gradients by hand. So this is now very simple. You just say, okay, there's a different type of layer. I'll just put them one by one, and then you flatten this all into like a single dimension. So you can make the math how many what the output size is going to be and how many channels you have. Like in the last convolutional layer, we increased the number of slots on statements about the image you can make to 32. And then in the end, basically you have like 512 inputs about the global image. And then we have like a simple neural network, which in this case is just like a linear projection. And this will then give us our kind of categorical output, right? So this is for MNIST, we had like 10 outputs that we want to have, so 0 to 9. And so this is kind of the last thing that does the final decision making, and it's very, very simple. It's not even like an MLP in a way. It's just like a neural network, like a linear projection. And so most of the work is really done by this local processing. Okay, so then for our MNIST, it was 28 times 28 pixels, a channel. We had 123 images kind of in our batch. And then once we run it through a network, we have for every image, we have our 10 probabilities for each of the categories. And so this is a very efficient way to do, for example, MNIST classification, the same thing you did in the exercise. And so you can now see kind of what is the effect of kind of adding all of this domain knowledge into the neural network. And you can see that it very easily outperforms even very, very large multi-layer perceptrons. So even very deep and very wide kind of standard neural networks. So here's an example with 100,000 parameters. And so this is in orange. And so you can see this is in the dashed line is the training loss, and the solid line is the test loss. And you can see that the CNN with like a tenth of the parameters easily outperforms this kind of dumb neural network. So remember what the kind of discussion is about universal function approximation. So it's not that the MLP is bad. I mean, it's a universal function approximator, but then in order to learn it, you need a lot of data, basically infinite amounts of data and exponentially more data. And we talked about how to choose the width or the depth of the neural network. And so we already figured out, okay, deep networks are more efficient than wide networks, but only having deep networks and not doing anything is also not great. So you can now add some more domain knowledge, and then you can easily beat even just deep networks with many, many parameters. All right, so then how does this look like kind of in terms of like translation, equivariance, and invariance? And so one of the, so there are these two things. And so equivariance basically means that your response is going to be kind of behave the same way when you move the input. So when you're saying, okay, I move my input like this rook to the right, so where should the signal be once I apply a convolution? This should also move to the right. So it shouldn't be like an invariant output. So like if like the response of the node is, okay, there's like a cat in there or like a rook in there or whatever, like that response should move together with the input. And so this is not invariance, but it's equivariance, right? And so the way that we express this is that, so we have a function and we have, so f of x. And so we, apply some kind of symmetry transformation on the input, and the same type of symmetry transformation should also be applied to the output. And so this is what we call equivariance under a symmetry group. And so basically what it should mean is that it doesn't matter. Do you shift first and convolve second, or do you first convolve and then shift? And so this is, these two operations should commute, right? And so convolutions, like just applying the filters, are equivariant operations. And the invariance in convolutional neural networks comes from the pooling operation, because if you do lots of equivariant stuff and then you start pooling, the field of view of the later nodes is going to be larger, and then the final statement is going to be, okay, is there 9? This should of course be invariant to where the 9 is, but where the edge is, in order to detect the 9, this should move together with the input because this is going to be an important signal. Okay, so then how do you get from equivariance to invariance? So this is exactly this thing. So of course, if the question you're asking is not, okay, where is the edge, but the question you're asking, is there a cat in the picture? This should now not be equivariant, but it should be invariant. And so here is basically, we choose a particular representation of the symmetry operation. So it's like a special case of equivariance where the kind of implementation of this symmetry operation of shifting to the left or to the right is associated with the identity transform. And so then basically what you're saying is, okay, the output of x and the output of the transformed x should be the same. And so then this is called invariance. And so the more general principle is equivariance, but then in equivariance you always need to choose, okay, how do I represent a certain type of operation that I put on the input? How do I represent this on the output space? And so if you're kind of familiar with group theory, so this is exactly the same type of representation theory. And invariance is the specific choice of not doing anything on the output and then requiring that the output of the transformed variable and the untransformed variable should be the same. All right, so then we can learn this, and then what type of filters do these convolutional neural networks work? And so this is a very kind of used to be state-of-the-art convolutional neural net. So it's called the Inception network. And so here, so I didn't really discuss what these. So it's an even more complicated structure, but the idea is the same. It's a convolutional net. And so here you can kind of see what is happening early on. And so early on, it's really kind of extracting very basic informations about the images. Learning color contrast. So it's learning filters that detect like a change in color. It's detecting these line detectors, so edge detectors. You can so we had like the horizontal edges and the vertical edges, and then you can of course have edges that are oriented in either direction. You have textures on the right hand side. So what is like the texture, like if it's like a fur detector and things like that, and so on. And you already started doing curves and so on. And so you would not come up with these convolutions by hand, right? And so this is the power of machine learning. You set up like the structure is kind of like a curriculum. Like, okay, this is how I think the neural network is going to learn efficiently, but then you leave the learning up to the data and up to the learning process, but you will kind of set up the right scaffolding. Okay, then once you move deeper into the layer, you become much more complicated. So you have kind of things where nodes that are sensitive to having like a certain color in the middle and a different color outside. You have these brightness gradients, more complicated curves, and so on. And so you kind of build up more and more complexity. If you move higher, then you get even more complicated things. You have like a proto head. So there's like certain nodes that because now as you're pooling, you have like a wider field of view, and so you can basically have nodes that are very kind of efficient at recognizing certain types of noses and so on. And so how this interpretation is being done is a separate lecture, but you can kind of basically say, okay, I look at this node and I can maximize the input to see what type of input image is going to maximize the response, this activation of this node. And so this is how you can try to interpret what is happening in this same way that you would maybe do like a brain scan, and you try to see what is happening in your own response. Okay, then later on you become much more complicated, and then you have very high level concepts deep in the network to see what is happening. And so there it's like distinguishing between different types of ears and so on. And so I encourage you to click on this link, and it's a very fascinating topic to try to learn kind of what is happening in these types of computer vision models. Okay, then one thing that is interesting, so you might know this thing, so you can kind of see, okay, what is happening in the prediction. So what do you see here? Anybody? So the computer says it sees a rabbit. And so let's see what is happening as you're rotating. So it's still a rabbit. So now it's not sure what's going on. And now it sees like a duck. Duck. And now it's a rabbit again. Oops. So you can see, okay, the response of a convolutional network is not, it's translation invariant, but it's not rotationally invariant, but it's also not clear that it should be rotationally invariant. For some things, it should be rotationally invariant, or like you want to have like, of course, like an edge, you want to have like the horizontal edge and the vertical edge, but kind of the overall response, like the world is much more translationally invariant than rotationally invariant, right? So we're walking around the world, we're not kind of doing somersaults all the time. And so kind of our vision is also adapted to this, but it's interesting that this is not kind of really hard-coded into the network. And so in order to compensate for this, so like in some ways you don't want to have it, but then for other ways you do want to have it. And so for things so the translation invariance we hard-coded into the network, but then for things that, where there are symmetries in the data that you, don't hard-code into the architecture, you need to spend compute to learn these symmetries, at least in an approximate way. And so you can see that in these kind of filters that are learned in neural networks, it will basically spend these slots that we kind of allocate in order to learn representations of the data, in order to do like an edge detect in this direction, this direction, this direction, this direction. I mean, you need to spend a lot of things because you didn't kind of spend the time to hard code it into the architecture. So this is again this trade-off between learning things from scratch and putting what we call inductive bias into the network. If you would have a network that is by definition rotation invariant, you wouldn't need to spend weights to make it rotation invariant. But here, because convolutional nets only are kind of translation invariant, the network will spend compute and weight and parameter space to allocate different edge detectors in different orientations, because it's important to kind of see what's going on in the image. All right. So then what's kind of fascinating, so why are convolutional nets? So you might think, okay, the way that we motivated this from like computational efficiency and so on, but actually it's very closely linked to kind of what happens in biology and like in actual vision in animals. And so it's one of the few ways where neural network, this connection to artificial brains and so on becomes somewhat real, right? And so I usually kind of recommend to not kind of take this like artificial intelligence or this brain analogy too seriously. It should be more thought of like matrix multiplication and information processing. But convolutional nets are one of the few cases where this really becomes relevant. And so you can see, so I'm not sure if you'll be able to hear this because
David Hubel of Harvard won a Nobel Prize with his colleague Torsten Wiesel for mapping the action of receptor cells along the visual path of a primate, from the retina to the cortex.
Receptor cells usually in the visual pathway mean the cells that take in the energy into electrical signals. And in the retina, those are the rods and cones. There are 125 million rods and cones in each retina. So in the case of the visual pathway, you start with the retina. The output is the optic nerve, which contains 1 million fibers. They end up in a certain region in the brain. That region, or there are really 2 or 3 regions that they end up in.
In this experimental footage, a bright vertical line stimulates a small number of neurons in the visual cortex of a cat. The crackling sound is the electrical activity of these neurons as they respond to this retinal image. By listening to the intensity of this electrical activity, the researchers can determine the correct orientation of the line. When the line is moved to a diagonal or horizontal position, the amount of stimulation decreases dramatically.
We're only at a very elementary stage when it comes to understanding something like how you recognize a face or something like that. The general region of the brain is known where things like that go on, but we don't have the slightest idea what's happening at the level of single cells for that particular problem. But for more elementary problems, for the very first processes of vision, we do have a very good understanding of what happens at the very beginning. So it's just a start.
Okay, so I'm not sure if it's the sound was doable, but so you've seen that basically it seems like cats, they also have these orientation dependent responses, right? So if you have like an edge which is going in one orientation, there's a response. If it's somewhat changing the orientation, it's not having a response. And it actually turns out they have like the same type of convolutional edge detectors in their early vision. And so the early points in vision where you're just kind of processing the raw information seem to be very similar. What is happening later on, he was saying, wasn't so super clear. And so then, okay, you can say, okay, that's amazing. So it's very similar to biological vision. We somehow figured out how to do vision, but if you take this too literally, then you also becomes very misleading. And so if you run this left image through a computer vision system, it will basically tell you it's a magpie, which is, if you don't know, this type of bird. And so clearly it's not. So there's clearly something that is not doing the same thing in human vision and in these artificial computer vision systems. And even though that we know that kind of the early kind of like the basic principles are similar. And so it's important, even though we kind of tell us the story that it's like about information processing, data representation, and more and more hierarchical reconstruction of what is in the image, that's what really happens in these networks is still an open question, and something that people are working on and trying to find out. Okay, so one of the examples, like another example from the first lecture, is that convolutional nets can react to signals that are imperceptible to the human eye. And so this is, I think, an example I already gave in the original lecture. So you have your panda, and then you just add noise, and then it completely changes its prediction to a different animal, like a gibbon. And so as a human, you might say, okay, that's ridiculous. Okay, what's happening here? But it's another indication that what happens in this computer vision systems is different than what happens in our own biological vision. Okay. So then the question to you is this a dog or a cat? Anybody who's for dog? Who's for cat? Okay. So this was originally a cat, but it was adversarially modified to basically, it's an adversarial attack on your brains. So that there's like some noise added to this image that made you unsure whether or not it's a dog or a cat. So if you just look on the left-hand side, I think everybody would have, raised their hand that it's a cat, right? But by just changing very imperceptibly certain things, it's, your own kind of biological vision system changed its prediction. And so it's kind of interesting that here you see, okay, that's ridiculous, but actually you're also perceptible to these types of mistakes. And then it's a question, okay, the more and more you rely on computer vision systems and self-driving cars and so on, of course, like these types of attacks where so this is specifically engineered in order to fool you. And so if you can specifically engineer to fool like a computer vision system that is in a self-driving car, of course, it's a big problem. Okay, but this is just to say it's not so easy to say, okay, computer vision is stupid. It's easy to fool ourselves as well. Okay, so then we can wrap it up so we can put it all together. So we had two topics basically in this lecture. So we had these residual connections and convolutional networks. And so these ResNets, which were one of the leading architectures for computer vision. And then, so this is a couple of years old. So by then there were lots of new architectures, but recently there was a network called ResNext. And so it's kind of regained the crown in computer vision, and it's kind of, based on the same type of principles. And so the architecture basically looks like this. It combines these convolutional ideas and the residual connection ideas in order to build a very deep model. So the basic kind of repeatable block. So it's the same idea when we started doing our kind of stacking operations with like batch normalization, nonlinearity, and so on. But now we add convolutions to the mix. So we have our 3x3 convolutions. We have a batch normalization. We have our nonlinearity, another convolution, another batch norm, and then this is the thing that gets skipped with the residual connection. And then you can stack these things until you have like a lot of different filters learned. And then at the very, very end, you kind of pool everything together, and then you have a fully connected network, which is this FC, in order to do the final prediction of what is in the image. And so this is what a modern computer vision system looks like. And so an exercise, what you'll do is you'll not train one because it's you need a GPU to train these kind of efficiently. We don't have enough time, but what we'll try to do is to download from an open repository, like a pre-trained state-of-the-art computer vision system. You just run it on a couple of input examples to see that you can actually do quite complicated prediction tasks, and not only see what type of digit is in a kind of handwritten 28 by 28 pixel image. Okay, so that was it for this week, and then see you at the exercise on Monday. Any questions? Yeah. So I think it's like I need to look myself. So I think it's so the story is basically, so we'll get to this. So like the next architecture, so there was like convolutional nets, and then the next architecture was so-called transformer networks, and they basically they removed a lot of like this nice domain knowledge. So here it's like a very convincing story that we put in our domain knowledge, and needs to be translation and variant and so on. Turns out if you have enough data, all of this doesn't matter anymore, and you can just do a kind of much more dumber architecture. And so I think it was basically just doing the same thing. It was just tuning a lot of like the small engineering details that kind of happened since ResNet 18 until transformers, like how you learn how to train these on these very, very large data sets. It was kind of engineered more precisely, but I don't think there was any kind of core architectural change, but I would need to look it up. Yeah. 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 So one of the interesting, so I mean, in a way, of course, you could say that's okay. What is the difference between like a sensor that we have, like for example, in particle physics, like a calorimeter? It's also kind of like multiple, like you have like intensity there, and then you have like a somewhat regularly arranged set of inputs. And so yeah, so people try to do convolutional nets for recognizing is there an electron in the sensor, right? And so one of the things that's kind of interesting for some of these use cases, I mentioned that this processing is independent of the number of inputs. And so it doesn't really matter what the kind of pixels are. So sometimes people do, let's say I have like 10 particles, and then for every particle, I have like 5 features. So I know whatever their position and their speed and whatever. And now I want to process like my field of view of 5 particles. So that doesn't really have anything to do with like local neighborhood. And it's just like an efficient way to do like a variable size input. And so then you basically say, okay, you just look at these particles, 2 particles at a time. Whether or not it's really important that you look at the local neighborhood might not be super important, but it's an efficient way to have like a variable size, input, because sometimes you might have an image with like 5 particles, you might have an like an event with 2 particles and so on, and you don't want to retrain like a network for 2, for 3, for 5. And so, for example, particle physics, we use convolutional nets to just process a variable number of a list of particles. And because of this pooling, somehow you're funneling this information to like a final classification anyways, and you just kind of use this local processing just as an efficiency measure. And like, but you see then like all this like nice story kind of basically drops down. Okay, any other questions? We're 2 minutes after time. No, actually we had some more time. Okay, I was timing it differently. Okay, fine. Okay, then we'll just end there. Yeah. Yeah. How are they chosen? So this is a bit of art. So so you can kind of see in the ResNets kind of here. Yeah, so you can kind of see what the type of convolutions are. So here it's like only like 2x3 convolutions all the way down, right? And then sometimes people use like bigger convolutions later on, but it doesn't really matter because like the more deeper you go, then so this idea that you're kind of become sensitive to like a bigger field of view will just happen a bit later in the network. So it's the size of the kernel is maybe not the most important thing. And so here with 3x3 convolutions, I think what we had with the kind of interpretable thing, where is it? Trying to find. Yeah, so here, so this was from this Inception network. There they had like 7x7 kernels. So it's not the most important choice. Usually you just try a few I mean, it shouldn't be 2 by 2. Because you need to have like enough kind of local context to do more complicated shapes, but it's also not like 100 by 100. So usually it's some low number. Yeah, it's 5 times 5. Yeah. All right. Any other questions? Yeah. Yeah, so this is an interesting concept. Then the question is, okay, what do you do? This is going to be in the future lecture. So what do you do if you don't have pixel data, right? Or you want to somehow, your notion of the neighborhood is somehow different. So, like in one dimension, this is closer. And so this is the case, for example, if you have, I mean, let's say you have like an experiment where you arranged your sensors in a grid, but maybe for local constraints, you don't have them exactly like on the grid, but they're like roughly somehow positioned. There's still some notion of neighborhood, but it's like somebody else needs to tell me, okay, what is my local neighborhood? And so this then leads to this concept of graph neural networks, which are kind of like an extension of convolutional neural networks. So in graph neural networks, you basically have your sensors, and then but by some other mechanism, you specify what is my local neighborhood, and this would then also kind of extend to like triangular neighborhoods, which is maybe a not so common choice, but it's like oftentimes you have like some notion of closeness, and this will then determine a graph, and we'll discuss this in a future lecture. But it's like an entire field, so it's graph neural nets. Yep. Yeah, so I can probably send something around. Yeah. So there's a very nice book on group theory for physicists that I can recommend. Yeah, also if you're a particle physicist, you should know about group theory. Okay. Yeah, but it's also like, so this type of formulation for symmetries in neural networks, so I mean, translation invariance is only like the first thing you want to do, right? And so then you might think, okay, so for vision might not be important, but for other things it might be important that you have like actually rotation invariant, or like in particle physics, there's a thing called like gauge symmetries. So and so there you want to have maybe neural networks or like Lorentz invariant, like if you have special relativity, it's so this is probably where you have seen group theory at some point. So when you did like special relativity, you had like Lorentz boosts that are like generalized rotations, right? And then like the combination of two Lorentz boosts is also Lorentz boost, right? And so group theory is basically you say, okay, like the multiplication of a thing is again like a thing in this like general group of operations. So two rotations after each other are also rotation. Or like linear maps, as we've seen with, if you don't add a nonlinearity, like the composition of multiple linear maps is also linear maps. So linear maps are also a group. So the group of matrices, so it's a group. So then the question is, okay, how do you specify, or how do you represent a group? So I can like reason abstractly about, two rotations should also be a rotation. But then how do you, so if I give you some concrete thing, what does it mean to rotate? And so this is then what's called the representation. And so then it's, we basically represent a rotation as a matrix. So if you have like orthogonal matrices with like cosine and sine and so on with angles. Yeah, you just need some mapping. So you need, a representation is basically a mapping from an element of the group. So I say rotation by 45 degree to like an actual like implementation of this thing in a kind of linear algebra way. So from my abstract thing to a matrix. And so then you basically have this matrix, but this doesn't need to be a bijection. For example, for the invariance, we're mapping any rotation to the identity, right? And so then basically what happens, you get invariance, right? So if the basic representation of the output is like what's called the trivial representation, any type of thing gets mapped to the identity, then basically you get invariance. And then the question is, okay, what happens if you add or multiply multiple things that belong to different representations and so on? So it becomes complicated, but at the basic level, it's like reasoning about like algorithm and having different implementations of it. And so that's the representation. Okay, cool. Excellent. So then we finished early. So I thought we finished at 12:30 or 1:30, but okay, my mistake. Okay, excellent. Have a good weekend and see you at the exercise on Monday.